Okay, alright, so let's go ahead and begin our next video. So this one should be a little bit faster, and you will find that this one is probably more helpful. So we're going to begin this video by just going back to Organic Chemistry 1 and just thinking about how we can prepare alcohols to get them ready for chemistry. So whenever we have a primary alkyl halide, okay, this could be chlorine, it could be bromine, or iodine, but we usually don't pay any attention to fluorine ever. And if we treat it with a small and strong base like sodium hydroxide, it simply performs a backside attack and in the process kicks off chlorine. Okay, so that chlorine will complex with the sodium and form a salt, and then we just simply substitute the hydroxy group or that alcohol in the position of chlorine. That would be a bimolecular substitution reaction. If, however, we had a tertiary substrate, we would have to go through solvolysis, okay, which is dumping this molecule in a bunch of water, and more specifically hydrolysis. We want hydrolysis, hence we put the hydroxy group on there. Okay, this would be an SN1 reaction. We're going to substitute the OH, or that hydroxy portion of this alcohol derivative, on to that position where the chlorine once was, and in the process we're going to go ahead and form an acid. So this is from chapter 7. These are ways that we learn to prepare an alcohol. Some other ways that we can prepare alcohols quite simply are from an alkene. So in this case we are given propene, and if we use a dilute acid such as sulfuric acid or even phosphoric acid, that would be H3PO4, then we are essentially abusing Le Chatelier's principle, and the dilute acid will move in the direction of forming the alcohol. Um, what's important to know here is that this can rearrange since its intermediate has a carbocation, okay? But for this case, if we treated propene with dilute sulfuric acid, that's called acid catalyzed hydration, then we will move in this direction to form the alcohol. If, however, we had a very concentrated acid, so there's a high hydronium concentration, let's say, then we would move the opposite direction. If we look now at this reaction, termed Oxymercuration Demercuration, then we will note that there is no rearrangement in this reaction, and you simply look at the alkene and put a hydroxy group at the most substituted position, right? You don't want to put it right here on the end because then it would be a primary alcohol. You want to put it right here on this portion of the alkene because it is then secondary, so it's at the most substituted position. So you would treat that with this mercury reagent in some water, or you could choose methanol. Okay, if you choose methanol right here, you would form a methoxy group. So you remember that from our alkoxy groups. If I put ethanol right here as the solvent, then we would have an ethoxy group at this position. But since we chose water, we have a hydroxy group right here. And then that second step is treating it with a reducing agent, but that we will learn about quite soon. For this reaction down here, another way to prepare an alcohol, but let's say that we wanted to make sure that it was at the lesser substituted position, we can employ something called Hydroboration Oxidation, and this is a very, very useful reaction. It's BH3 complexed with tetrahydrofuran, and then we put it with some peroxides in a basic environment. You can also write BH3 as B2H6. That would be diborane, and that's really what it is, but then diborane splits up into a bunch of these BH3s, okay? So these are just some possible reactions from Organic 1. They're all probably going to pop up at some point, but this is how we can prepare an alcohol from different kinds of alkyl halides, and how we can prepare an alcohol from just a simple alkene. As for preparing alcohols from alkynes, I'll leave that up for you to review. You can find that in chapter 9 of the book that I put on D2L. So let's continue here. And let's go ahead and just sort of shift gears for a moment. After watching the first video, I talked a little bit on naming, so we're going to go ahead and do all of these examples and see how we feel with them. So I'm going to go ahead and switch over my camera, and we're going to work on these all together. But if you'd like to at this moment, pause the video and see if you can name all of these molecules on the left, and you can draw these molecules on the right. Okay, so pause the video now if you don't want to see it. Okay, so let's begin, and we're going to go ahead and attempt to uh, draw or name all of these molecules. We're going to start with the structure to names. So we'll start with the structure to the name. And for this first molecule, we had this six-membered ring with a alcohol that is a hydroxy group, and we had it with this OCH3, which is a methoxy group. So it would probably be good at this point, after watching the first video, you now know what these kinds of groups are called. It would be good to sort of label them. So this is referred to as a methoxy group. Okay, methoxy group. And this one is a hydroxy group, okay, but in general it's an alcohol, but we'll just say that it's a hydroxy group, okay? So where are we gonna start numbering? Are we gonna start numbering from the methoxy group or our hydroxy group, namely the alcohol? Now, what's important to keep in mind as well is that this is an alcohol. This methoxy group, though, is not an alcohol. So alcohols get our first priority whenever we start numbering things. So we would start from the alcohol and number our way over to that methoxy. Okay, we'll take the shortest path, right? We don't want to go down here around this way. We would rather go this way. So let's go ahead and put it all together. We know that cyclohexane is our parent chain, okay? And in fact, we have a cyclohexanol, right? It's cyclohexane with the alcohol, so this is a cyclohexanol parent. And you can say that at the third carbon, we have our methoxy. So you can term this one 3-methoxy. And you can, if you want to put the number in there, you can, just to be safe. You can say -1 cyclohexanol. The 1 and the OL at the end, the ol, indicate that the first position we have the alcohol, and cyclohexane indicating that we have the six-membered ring. So if we look at then that next example, or the molecule right next to this one on the PowerPoint, we see that we have an alcohol which is directly adjacent to a methoxy group. So we have the hydroxy and the methoxy. So this one would simply be 2-methoxy, 1-cyclohexanol. So this one would be 2-methoxy 1-cyclohexanol. In addition, if I was to actually name this, this would now be 2-ethoxy. So this is an ethoxy group. Okay, should be referred to as an ethoxy group. So if you remember, these groups, ethoxy, hydroxy, and methoxy, are all what we refer to as alkoxy groups, okay, or alkoxy chains, but they're alkoxy groups, okay. We're now going to name the two molecules at the bottom. So the first one that we have is written out in a sort of condensed form. And we can see that at the first and the second carbon, we have an alcohol, okay? So I'm gonna go ahead and just convert this into the skeletal structure so that we can probably see it a little bit better. And if I convert it into that skeletal structure, I have my CH3 right here, I have a CH2 right here, and then I have a CH right here. So this middle carbon has an OH, and this terminal carbon also has an OH. So I'm going to go ahead and draw those in. Whenever a compound has two alcohols present in it, we refer to that as a diol. So this is a diol species. Okay. And they're quite simple to name. So we say that let's start numbering our carbons insofar that we give the alcohol group the lowest priority, okay, or the highest priority, but the lowest locant value. So this compound, we know that it's a diol. The parent chain is propane, and those alcohols are occurring at the first and second position. So this molecule will be termed 1, 2. So at the first and the second position of my propane, I have my diols. So it's 1, 2 dash propane diol. Pretty simple to name. 1, 2 dash propane diol. Okay, so let's continue. We now have this compound right here, and we have added an alkyl halide, namely iodine, and we have this alcohol near the end of our molecule. So now that things are beginning to get a little bit crowded, it would probably be best to label things and just be a little bit extra. Okay, so I'm going to go ahead and mark this out for you in just a second. So our first challenge here is we want to find the parent chain, right? That's what we first want to do. And we can see that it would start right here, and then it would move over like this. So this is my parent chain. I'm going to go ahead and just sort of bold that in a little bit. But you can see that our parent chain follows this, goes down here, comes back up, and goes back down. That's our parent chain. So anything else that is not a part of that parent chain is going to be a substituent. So this iodine is a substituent. This methyl right here is a substituent. And this hydroxy group is also a substituent. So if I start numbering it to where I give the hydroxy group the first priority, because this is the first thing that I need to start numbering to. Alcohols are the most important in our chain. I'm going to go ahead and number this. We have it just like this. So we have a pentane. In fact, we have a 2-pentanol. 2-pentanol is going to be our parent, okay? 2-pentanol. The 2-ol indicating that we have at the second position in alcohol, and the penta, the pentane, indicating that we have a 5-membered chain. At the second position, I have a methyl, so I have a 2-methyl. And at the fourth position, I have an iodo. If I put this all together alphabetically, I'll have 4-iodo, dash 2-methyl, dash 2-pentanol. So let's go ahead and put that all together. 4-iodo, dash 2-methyl, dash 2-pentanol. That is the molecule that I have there. We're going to go ahead and move on, and we're going to now go from the name to the structure. And I'm going to start with those 2 diol compounds. So we're going to start with the 2 that Duff has given on his exam before, which is 3,3, and 3,3 dimethyl dash 1,2 dash butane diol. And then the other compound, which is 3,3-dimethyl -1,2 pentane diol. These are very, very, very similar. So let's start with this molecule up top. Let's start with the butane diol compound. Here's how you can logically read this. Your parent chain is butane, and there's two alcohols in it, which are at the first and second position. I'll say that one more time. My parent chain is butane, and at the first and second position I have alcohols. There we go. There's the first and second position, and I'll just label them just so that we can be quite scrupulous. And at the third position, okay, I have two methyls. So I have a methyl right here. I'll put them in green. There's one methyl, and there's another methyl. So this right here is at the, here's how you read this. At the third position, I have two methyls, hence the 3,3-dimethyl. And at the first and second position, it constitutes my diol with those two alcohol groups. If you wanted this compound on the bottom, it would be as simple as simply making this a 5-membered ring. So this right here is the one on top. If you wanted the one on bottom, you simply just need to add an additional carbon. So we've answered those two. Let's now look at the top compound, which I actually gave you a condensed structure for, so we're going to need to work out that one. But it's KOCH2CH3. And then I want to look at lithium butoxide after that. So we'll look at this one, and then we will look at lithium butoxide. So if we start with this one up top here, we will notice that we have a K, which is a spectator ion, which is directly next to this oxygen. So do you remember what I said about if there's a spectator ion, that spectator ion acquires the positive charge, and the thing right next to it acquires a negative charge. So this can really be shown as so. It can really be shown as a potassium with a positive charge right next to an oxygen with a negative charge. So we have an alkoxide. Okay? Remember from our first video we have an alkoxide. And it's attached to this ethyl group right here. So this is an ethoxide ion, okay? This is an ethoxide ion, or what we remember, it is generally called an alkoxide ion. So this is an alkoxide ion. That is a alcohol which has lost its proton. In general, this whole compound right here is called potassium ethoxide. So this compound is called potassium ethoxide. Potassium ethoxide. So we've now just seen how to go from the name, or from a half condensed structure to a skeletal structure showing charges and such to the full name. So in general, this thing is called an alkoxide ion, so it's really potassium ethoxide. We'll look at this other example that has been asked of you to draw. We have lithium butoxide. So that means that I need a butane attached to my alkoxide ion. And then there's a lithium sort of just spectating. So let's draw the lithium spectating right here. Here's the lithium. It's got the positive charge since it's a spectator. And I need the alkoxide ion attached to a butyl chain. So here's my alkoxide ion. And it's attached to a butyl chain. So I'm going to have 1, 2, 3, 4. This right here is lithium butoxide. Okay. You can also show both of these compounds in general as so. You could also show them as KO, just like that. And you could show that lithium one as LiO, just like so. You could even show it as LiO CH2, 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 CH3. And you can show this compound right here as KOCH2, CH3. There are many, many ways to show this. Okay. So now we've learned how to go from the name to structure and vice versa of our alkoxide ions. And we've also looked at the diols. Okay, let's look at the last couple examples here. So we have isobutyl alcohol and we have 3-methoxycyclopentene. So we'll go ahead and do these. So we have isobutyl alcohol that we need to draw. And then we have 3-methoxycyclopentene. 3-methoxycyclopentene. Pentene. Okay, so isobutyl alcohol. It sounds like quite the challenge, right? Okay, so take it one step at a time. You know that you have an alcohol, and it's attached to some kind of butyl derivative. So we need the case where the alcohol is attached to an isobutyl group. Okay. Let's think about what types of compounds we do have, right? So we know that just a regular butyl chain is going to be 4 carbons, just like that. That's going to be a regular butyl chain, okay? And we'll just say that it's connected to some parent, okay? So the parent, here's the parent chain, is our first, second, third, and fourth carbon, okay? If we had a parent chain, however, parent chain, not an R chain, a parent chain, and we went off like this, so we sort of split that bond. This is going to be our sec-butyl. Okay, so this is going to be a sec-butyl. This one up here is just going to be butyl. We could also have the parent chain where it hits right here and then it comes off in a chicken foot manner. So that would give us the tert-butyl. This is a T-butyl or tert-butyl. So we're slowly working our way over to isobutyl. So if we look at isobutyl then, it's going to be a parent, okay? And we're going to connect our isobutyl chain. We're going to have 1, and then we're going to have our second carbon. So here's our first carbon, our second carbon, and then it isolates this group at the end. This has 4 carbons attached to it, and so we deem that an isobutyl side group, right? So then what has isobutanol got to be? Well, isobutanol is simply just going to be this isobutyl group, but the parent is an alcohol. So isobutyl alcohol is going to look like this. Here is my isobutyl group, and it's attached to an alcohol. This is isobutyl alcohol. Okay, let's now look at 3-methoxycyclopentene. And we know that just from reading this, our parent is a cyclic 5-membered ring with a double bond. So let's go ahead and draw that. Let's draw cyclopentene. So we draw our cyclic 5-membered ring, and I just put an alkene anywhere. I'll just put the alkene right here. Why not? It doesn't matter where I put it. It's a cyclopentene. That is my parent. Now, 3 positions away from where I start my alkene, I have a methoxy group. So I have to start numbering 3 positions away from where I start my double bond. So I'm going to start right here with 1, and then I'm going to go 2, and then 3. So I'm going to have 1, 2, 3. And at this position, I have my methoxy group. So it's an O attached to a CH3. That would be my methoxy group. Now, you do not start numbering right here closest to the group. You always start numbering the furthest away. So where you start that double bond, you would start here and then start moving up. You could have equally chose to start right here, call this 1, then this 2, and then this 3. That would have also been plausible, but I'm just showing it going this way. So that's how we name all of those such compounds. Okay, so that should be really good practice for you. All of these have appeared on the exam before. So let's now go ahead and switch back to the PowerPoint. And we're going to keep on moving ahead. We're going to ignore this for now, but we'll come back to it. And we're going to play a little game, and this will be our game called oxidation states. So we have heard plenty of times in organic chemistry or general chemistry these oxioreductase things, or what's oxidation, what's reduction, why does it matter, how can we use it, right? A seemingly very esoteric topic, but it's actually quite simple. So here's how we play this game, okay? Ignore this diagram unless you want to go back and read it. Just ignore everything and just hear me out, okay? We're just going to say that we have a molecule like ethanol, or I'm sorry, methanol. So here's my molecule. This molecule right here is methanol, right? Methyl chain attached to alcohol. This is methanol. And I'm going to look at that central carbon, okay? We're talking about oxidation states whenever we're just trying to look at what that carbon is connected to, okay? So we're looking at this center carbon and we're treating him as the big player in all of this, okay? Now, if there is a hydrogen connected to a carbon, we're going to give that carbon a -1. If there's an oxygen connected to the carbon, we're going to say +1. And if there is carbon attached to the carbon itself, so if there's a carbon and then a carbon, we're going to go ahead and add 0. So we're going to sum up all of these possible values that we can get and see what our value is. So let's just look here, okay? Again, remember, hydrogen is -1 and an oxygen is going to be a +1. If I look right here at this carbon, it has a hydrogen, which is a -1. Then we have another hydrogen, so now we're up to -2. And it has a third hydrogen, so we're up to -3. Then we have to add 1 because of this oxygen. So what is the -3 plus 1? That's -2. So our oxidation state is -2, okay? Let's look at this one now, this compound, methane. There's 4 hydrogens attached to this carbon, and each of them count for -1, so that'd be -1, -1, -1, -1. That's -4. Okay. So let's keep playing this game. Now we have formaldehyde. So form or formal groups are typically 1 carbon groups, but we have formaldehyde here. And it's connected to how many carbons? That's 2, right? So this one has a -2 from the hydrogens. So let's put up a -2 here. And then it has 1 oxygen, but we're really treating this as like 2 oxygen bonds, okay? Every single bond to a hydrogen or oxygen or carbon that we make counts as a +1. So this one has a +1 from one of the pi bonds and then a +1 from one of the sigma bonds. So this really doesn't just constitute a +1, but it constitutes +2. So we have our -2 from the hydrogens, and then we have our +2 from this carbonyl moiety. -2 plus 2 is 0. Let's look at formic acid. we have 3 bonds to oxygen, so that will give us a +3. And then we have this 1 from hydrogen, so we have to -1. This is +3 take away 1, that gives us 2. And look here, every single bond is made to an oxygen, so we give it a +4. What is happening in this direction right here is what is called oxidation. The opposite direction, reduction. Okay? So you can see that this carbon is becoming more and more oxidized. Okay? If you'd like a very in-depth explanation, you can read the book and check out the slide or the page with this, and it'll tell you a little bit more about how that exactly works. But for us, our quick go-to is going to be looking at these numbers and saying that if the number is more positive, right, it's going to be more oxidized. So you would say formic acid here is more reduced than carbon dioxide, and carbon dioxide is more oxidized than everything else here, right? You could say methane is the most reduced molecule out of all of these, okay? It's not oxidized at all, okay? Methanol is a little bit oxidized, but it has a -2 oxidation state. So let's go ahead and move forward. So now we have this new toolkit. We now know how to identify the oxidation states and see what's more oxidated or reduced. So let's now play this game one more time. We have this right here. And do you remember what I said? If a carbon was attached to another carbon, we just called it 0. So here's my central carbon right here. Here's my central carbon. And it's connected to a carbon on the left, a carbon on the right. So they both count for 0. This is 0 plus 0. This oxygen right here has 2 bonds to it, so we're going to give it a +2. Now if you look over here, we still have these 2 carbons attached, so that's a +0 from this guy and a +0 from this guy. And then what about this? Well, it's still 1 bond to oxygen and another bond to oxygen, so this one will give us a +2. These are in fact the same state of oxidation. They're both equally oxidized. So if you were asked a question like, did this undergo an oxidation, or did it undergo a reduction, or neither, you would say neither. Okay. So let's go ahead and go through all these really quickly. It'll be good practice and you'll see it on your exam. So we have now introduced these halogens in here, and we'll see how they come into play. But just to put it out there, if you have an halogen, which I'm just going to call X, it is also going to act just like an oxygen, okay? Not a 0, and it's going to act like an oxygen, okay? It'll give you that +1. So just keep that in mind, okay? Oxygen and the halogens will also give you a +1. So we look over here with this compound. It has a 0 plus a 0 plus 2. So we have a +2. Right here we have a 0 plus a 0 plus a +1 plus 1. This is a +2. This is neither reduction or oxidation. They both have the same oxidation state. If we look at this compound right here, okay, we have 1 carbon, which will constitute a +0. We have a -1 from this hydrogen, and we have a +2 from the 2 bonds that go to the oxygen. So this one will have a overall +2 -1, that's a +1 right here. If we look at this right here, we will see that we have 3 bonds to oxygen. That's a +3. And if you look, and then this carbon here, of course, constitutes nothing. So we went from an overall +1, right? Overall +1 on this side to a +3. This is definitely an oxidation. So we definitely had to oxidize to get here, okay? We definitely oxidize this molecule. And you can just sort of see it, right? You can see this thing turn into this, definitely oxidized. Okay, well, look, this molecule is the same one as this one. So I already know this one's going to be +3. Now, just by taking a wild guess, this one has more hydrogens than this guy. I bet you it's probably going to be a reduction. So that would be a bracket H, which means that we are adding hydrogens. That's the symbology that we use. That's the symbolism. But let's play the game that we have been playing. So we have a carbon which contributes +0. We have this oxygen which is going to contribute a +1. And then we have these two invisible hydrogens which will constitute an overall -2. So -2 plus 1 is -1. This went from a +3 to a -1. That's reduction, right? We reduced our value there. So just stop here for a moment and look at what's going on. You can see that it's all about the bonds that we're making to oxygen and hydrogen. And so you can just see right here, like you don't have to play with the numbers anymore. You can just see whether it was oxidized or not just by looking at it for a quick second. And look here, an aldehyde to a carboxylic acid, that increased your oxidation state, right? So you can see that you can just see the molecule get more bonds to oxygen. It's oxidized. You can see right here, those bonds to oxygen are being taken away. So it's being reduced. You can just see the oxidation or reduction. So let's go ahead and play the same game down here, but without any of the numbers. No +1, no -1, and no zeros. Looky here. We have 3 bonds to, right? Well, I'm going to call this all oxygen, but we have 2 to oxygen and 1 is chlorine, but they're all acting the same. And then we have 3 bonds to oxygen. This is neither reduction nor oxidation. These have the same oxidation state because there's 3 bonds to something here that isn't carbon or hydrogen, and the same case here. Let's look here. 1 bond to oxygen versus 2 bonds to oxygen. That means I went from a reduced state to an oxidized state. This was definitely oxidation. 100%, that's definitely oxidized. Play the same game that we have up here if you'd like to, but I guarantee you this one's going to be oxidation. Let's now look at this one. We have a cyclopentanone molecule with a lactone here, and 2 bonds to oxygen versus 3 bonds to oxygen. This was definitely oxidized. It gained more bonds to an oxygen or a halogen. So you see how quickly we can play this game. In fact, look at every single one of these molecules and you can sort of just see it now with your eyes. You don't have to play that numbers game, okay? And so these reactions right here, the oxidation ones, if they went backwards, those would all be reduction reactions. Likewise, if you had this ethanol and then you moved it over to acetic acid, so this went the opposite way, the opposite direction would then be an oxidation. Okay? So good. We now know how to assess these oxidation states and determine when something has went through the grinder and we've looked at its final product, whether it was oxidized or reduced. And this is very important for the chemistry that we're going to be doing. In fact, it's very important for your exam just to know this fundamental principle. So this is from your exam, and it says, which of the following is neither an oxidation nor reduction of the organic substrate? So let's go ahead and look here and see if we can do this together, okay? We have the same amount of carbons in both of these chains, right here and right here. The difference is that this one has 2 bonds to oxygen, and this one has 1, 2, 3 bonds to oxygen. I can tell you right now that this hydrogen became oxidized to become an oxygen. 2 bonds versus 3 bonds, it definitely got oxidized going to the right. That's definitely an oxidation reaction. Okay, let's now look at this one. A little bit strange, right? But let's just take a guess here, right? We haven't worked with double bonds yet in changing them to this, but I bet you it's probably an oxidation, okay? Because we're gaining bonds to oxygen. But let's prove it to ourselves, right? We know how to play that game, so we can use that to our advantage. So this molecule right here really looks like so, and I'll go ahead and switch this over just for a moment, but it really looks like this, okay? So we have this molecule, CH2. We have this molecule right here, okay? And the other molecule that we have is this one, okay? But let's play that same game that we always have. So, well, wait a second, Sammy. We have 2 carbons which are changing. Okay, that's fine. We're going to add up then this total sum from this carbon and the total sum from this carbon. So I'm going to go ahead and draw in all of the hydrogens explicitly. Just on those 2 carbons that reacted. And let's go ahead and play our game again. I'm going to start with the molecule on the left. I know that I have, let's start with this carbon. I have 2 bonds to hydrogen, which will give me a -2, so a -2 from these 2 hydrogens. And then I have a carbon double bonded to a carbon, so that contributes 2 of the plus zeros. So it's a +0 and another +0. So this one right here is a -2. If I look at this one, there is 1 bond to a hydrogen, and then there's 3 bonds to carbon. So that would be a +0, +0, and another +0. So we just have a -1 on this side. Overall, we have a -3. Okay, let's look at this guy over here now. We have a -2 from these hydrogens on this carbon, and then we have a +1. So this one's a -2 from the hydrogens, and then a +1 from that oxygen. We don't care about the carbon, of course. And we have a -1. Things are looking a little bit different. I can definitely tell you that this carbon was oxidized by +1. So it did become oxidized, but we have to look at the overall net molecule. Okay, so let's look at this one. We have 1 hydrogen and 1 bond to oxygen, so that would be a -1 and a +1. And then we have 2 bonds to carbon. So this one actually has an overall oxidation state of 0. 0 minus 1, that would be -1. -3 to -1, that means we added 2 going across. This is definitely an oxidation. So we have now just seen that epoxide formation, okay, oxidizes that molecule. So we've now proved it to ourselves. We know this, okay? We don't have to play that game, okay? So that's good. So let's go ahead and keep on moving forward, okay? And we have now said that this one is also an oxidation. Okay, let's look at this guy right here. We have 2 bonds to an oxygen that turn into 1 bond to oxygen. Definitely going to be a reduction here. You can see that, right? The aldehyde becomes now, I mean, it loses a bond to oxygen, right? It loses one of its bonds to that oxygen and gives it to another hydrogen. So it's definitely got reduced. Let's look at this last one. A double bond gets hydrated. So we put a hydrogen on one side. Okay, you see this was a CH2. Now it's a CH3. This one was a CH, but is now a CH with an oxygen. So that's a little interesting, right? One of the carbons got oxidized and one of them got reduced. So let's go ahead and run back to our sheet and see if we can go ahead and make sense of what's happening here. If we look at the molecule one more time, so I'm going to go ahead and draw it out here. We start with this molecule, and it turns into this. So it simply becomes hydrated, okay? We added an H on that side and an OH on that side. So maybe this underwent a a oxymercuration demercuration, or an acid catalyzed hydration. But let's go ahead and play the same game that we always have. So with this molecule, it's the same as the one right here, so I know it's -3, right? This and that, the same molecule. So let's call it -3. Let's now look over at this molecule, and I'll draw on all the hydrogens. So there's one, and then here's 3. So over on this side, I have a -1, -2, -3, and then I add the 0 from that one carbon. This right here is going to be a -3. Okay. And if I look at this carbon, it's connected to 2 carbons. So this is connected right here, and this guy is connected right there. So that's 2 connections to carbon. That adds nothing. It adds 0. And then from this hydrogen, I add a -1. And from this oxygen, this one bond to oxygen, I add a +1. What's -1 plus 1? That's 0. So the overall grand total here is 0 minus 3. Well, that's really interesting, Sammy. We got more bonds to oxygen, but it wasn't oxidized. Yes, that can happen, okay? And see, what you want to notice here is that on one side we added an extra hydrogen, which gave us that -1. And then the other side we added an oxygen, which gave us a +1. So we basically just said +1 on the left, -1 on the right. We added and subtracted 0 across the middle. So this is neither. Actually, you don't write anything. It's just neither. So it's neither an oxidation nor a reduction reaction. Okay. So let's now return to our PowerPoint. And this guy right here is going to be our answer. This one, 4 only, is neither an oxidation nor a reduction. So let's go ahead and move on. So now we know how to answer such a question on an exam. A little tricky there, but let's go ahead and move forward and see what else we can answer. So here's another way that Duff could ask such a question. And it's asking which is neither an oxidation nor reduction. Okay. So let's look here. We've seen this kind of problem before, haven't we? We've seen that carbonyl turn into 2 split groups. And so 2 bonds to oxygen turns into another 2 bonds of oxygen. This one is neither an oxidation nor a reduction. So this one definitely, right here, is neither an oxidation nor a reduction. Let's look at this guy right here. We went from 1 bond to bromine and 1 bond to oxygen. So that would be 2 bonds that give us a +1 to another 2 bonds that gives us those +1s. Okay. So this is a +1 and a +1 to a +1 and a +1. Interesting. And if you notice something here, I'll just go ahead and draw out the hydrogens as one line. So there's 2 hydrogens right there, 1 hydrogen right here. There's still 2 hydrogens right there, and 1 hydrogen right there. This right here, okay, is neither an oxidation nor a reduction. You can play the same game, but it's all about the bonds that you're making, okay? Hydration, though, like we saw in this last example, when you hydrate the molecule, that is add OH and H across the double bond, that is neither an oxidation nor reduction. We looky here, and we have this epoxide formation, and we can see that it is in fact still the -2 plus the 1, the -2 plus the 1, and then we have the -1 plus 1, -1 plus 1. Okay? So this is also going to be neither reduction nor an oxidation. Let's look at this last molecule here. And I bet you that we already know the answer. It's obviously 1 and 2. But this one right here is going to be an oxidation or reduction. Can you tell just from looking at it whether it's going to oxidize or reduce? If you said it's definitely going to reduce, that is correct. This reaction is a reduction of our organic substrate. So bracket H. We can see that we had one bond here to oxygen and another there, and we lost it at this carbon while this one maintained it. Okay, so let's go ahead and move forward. We're getting lots of practice. But here's another way that Duff could ask such the question at the beginning of your exam. We have a alkene species that becomes a diol. That's funny. It's like epoxide formation, but these, because we still have the bond right here and the bond right there, we have epoxide formation sort of going on here, but these oxygens now have their own separate hydrogens, right? It looks very, very similar to a double bond like so, getting that single bond from one carbon to an O and another single bond to a single bonded O, but we now just have it to its own respective alcohol. So this is diol formation. We could have used potassium permanganate. We could have used osmium tetroxide. You know that from your chapter 8 reactions, how to prepare a diol. And so I think that's going to be oxidation, right? We termed that epoxide formation to be an oxidation, and this one is also adding a bond on the left side of that carbon and on the right side. This has definitely got to be an oxidation. Prove that to yourself with the numbers if you'd like, but an alkene to a diol is going to be oxidation. Well, look here now. We have an epoxide going to the alcohol. We had just shown that an epoxide to one alcohol is a reduction. So an epoxide to one alcohol is a reduction. If, and I say if, this epoxide went to the diol right here, it would be neither. So if this guy right here, okay, went to him, it would be neither. Let's continue. Let's look at this guy. We have two bonds to the heteroatoms of different carbons, epoxide. This one's also neither. This one has got to be, I'll just draw N for neither. So question 2 says, which of the above represents a reduction? Well, that would be 2. There's my free points. And which of the above represents an oxidation? Well, that would be problem 1 right here. Easy points. Let's go ahead and move ahead. We now have reactions, but I'm probably going to group this into one video. I just wanted to get the naming and then the oxidation and reduction put into one video. So the next video will be over reactions. As always, thanks for watching.